Hello students, in this video we'll see an example of computing a real improper integral using the residue theorem. For example, let's compute the following integral. Let's compute the integral from negative infinity to infinity of x squared over 1 plus x to the fourth dx. That's a real integral, and if I wanted to do this with Calc 2 techniques, what I would do is I would basically use partial fractions on this, right? It turns out that partial fractions for this one is a little bit of a pain in the sense that I can factor 1 plus x to the fourth into two irreducible quadratic factors, and then I have a lot of terms to compute. There's a 4x4 system to solve, and so it's a little bit messy to do something like this. So I'm going to solve this problem using residues, and the idea is to extend this function to the complex plane and integrate over a correct contour. So what I'm going to do is I'm going to do this by consider the complex extension. Namely, I'm going to look at f of z, which is z squared over 1 plus z to the fourth. Now, this function, f of z, agrees with the integrand along the real axis, right? And the contour, this is a classic one from complex analysis. Here's the real axis. Here's the imaginary axis. And I'm going to draw this contour. It's a semicircular contour. Here is negative r. Here is positive r. I'm going to let r be a real parameter. R is a real parameter. Let's just say it's much, much bigger than 1. Okay? Like a 10 or 100 or a million, right? We're going to let go to infinity eventually, right? I'm going to draw a semicircle. And then my contour is going to be moving along the real axis like this, and then up along the semicircle. Okay? So this contour is two pieces. It's this piece down over here, LR, and this semicircle over here, CR. Okay? Now, if r is bigger than 1, this function has singularities in here, right? So f of z has isolated singularities when z to the fourth is equal to negative 1, which is the same as e to the I pi. And of course, I can find the fourth roots of negative 1. The fourth roots of negative 1 are what? The fourth roots of negative 1 are going to be what? Well, I would say it's this. It's e to the I 3 pi. It's e to the I 5 pi. It's e to the I 7 pi, and to find the fourth roots, we just take the fourth power of all these things. So those are going to be what? Those are going to be, I'm using De Moivre's theorem over here, just quickly, right? Because we're more advanced than that point in the course now, right? So there's going to be e to the I pi over 4, e to the I 3 pi over 4, e to the I 5 pi over 4, and e to the I 7 pi over 4. So those are the singularities. There are two singularities inside this contour. There's a singularity here at e to the I pi over 4. That's a singularity. There's a singularity here, symmetrically, e to the I 3 pi over 4. Two singularities to consider, that singularity and that singularity. So the residue theorem tells me what? The residue theorem tells me that the integral over LR of f of z dz plus the integral over CR of f of z dz, that's an entire closed contour, right? It's a closed curve over here, is going to be what? Is going to be equal to 2 pi I times the sum of the residues, right? So 2 pi I, and then I have to do the residue of f at e to the I pi over 4, plus the residue of f at the point e to the I 3 pi over 4. Beautiful. That's the answer. We're done. Not quite. We have to do some limits now, right? Now, I claim to you that this integral, as r goes to infinity, let's figure out what happens as r goes to infinity. As r goes to infinity, this integral over here is what? This is the integral from negative r to r of x squared over 1 plus x to the fourth dx. Beautiful. This integral over here, the CR integral, is equal to what? Plus the integral from 0 to 2 pi. Then I'll have an r e to the I theta, not 2 pi, but just pi actually, because I'm only doing half the circle. It's a semicircle, so we have to change that to a pi, not a 2 pi. So that's going to be a pi over here. Pi. It won't matter in our calculation. It's just a force of habit that goes to 2 pi. 1 plus r e to the I theta to the fourth, then r I e to the I theta d theta is equal to these two residues over here. So this is equal to this expression over here. So those two expressions are equal to each other. Okay, good. That's a little bit sloppy. So let's fix that. So these two things is equal to that side of the equation. Okay. Now, let's think about what happens to this as r goes to infinity. Okay, as r goes to infinity, what's going to happen over here? So as r goes to infinity, as r goes to infinity, the integral from negative r to r of x squared dx over 1 plus x to the fourth converges to the thing we want, right? Converges to negative infinity to infinity of x squared over 1 plus x to the fourth dx. Good. So when I let r go to infinity, this term over here goes to what we want. What about this term over here? What's happening? Let's think of what happens to this term over here as r goes to infinity, okay? Okay, there's an r squared on top, an r, so there's the r cubed on top, and there's a what in the bottom? There's an r to the fourth in the bottom. So if I put moduluses everywhere over here, what can I say? The modulus of the integral over CR of f of z dz is no more than what? Is no more than just the integral from 0 to, by putting the absolute value on the inside of the modulus on the inside, the modulus of e to the I theta is going to be 1, so all those i's in e to the I theta turn into 1s, and so I'm going to have a what on top? I'm going to have r cubed on top. Okay, beautiful. And then what on the bottom? I'm going to have a what? I'm going to, using the triangle inequality, I can say it's r to the fourth minus 1 d theta, right? And of course, this clearly goes to 0 as r goes to infinity. So this contribution tends to 0 as r goes to infinity. Okay, beautiful. Now, I should compute these residues. So let's recall. If f of z, which is p of z over q of z, has a simple pole, which all of these poles are simple pole at z equals a, then the residue of f at a is going to be what? Is going to be, well, if it's a simple pole, that means that q is 0 at a and p is not 0 at a, right? And so in other words, what that tells me is this is going to be p of a, the first term of the Taylor expansion, over the first non-zero term, q prime of a. Okay, that's a very, very useful formula because now we're able to do these residues. So in other words, what can we say? So let's compute these residues now. So what's the residue? So the residue of f at e to the I pi over 4 is going to be what? Well, I'm going to do this trick over here, right? I'm going to say it's going to be the top of e to the I pi over 4, so it's going to be e to the I pi over 4 squared over what? Over, now to do the derivative of this thing, so it's going to be a 4, and then it's going to be x cubed, so it's going to be e to the I pi over 4 cubed, okay? And then similarly, so what will this simplify to? This is going to simplify to just e to the I pi over 2, that's going to be an I over 4, and then what? And then this is going to be a 3 pi over 4, e to the I 3 pi over 4. Great. All right, and then the next residue, the residue of f at e to the I 3 pi over 4 is going to be e to the I 3 pi over 4 squared over 4 e to the I 3 pi over 4 cubed. Okay, so if we simplify this, what are we going to get? This is going to be what? This is going to be a, let's see. So this is going to be a, if I square this, I'm going to have a 6 pi over 4, that's going to be a negative I, right? Because it's going to be 6 pi over 4. 6 pi over 4 is going to be the same as 3/2, right? That's going to be a negative I, so I'm going to have a negative I over 4, and then what? And then this is going to be a 9 pi over 4, but 9 pi over 4 is the same in the integral as I pi over 4, so it's going to be e to the I pi over 4. Okay, great. Going to add these two things together. So of course I'm going to put this into a simpler form. I'm going to write this as I over 4 times e to the negative I 3 pi over 4. And this thing over here, I'm going to write this as negative I over 4, and then what? And then e to the negative I pi over 4. Okay, good. All right, and so now what's our integral going to be? So our integral is going to be these two things together. We're going to have to do a little bit of arithmetic over here. That's okay. And so let's figure out what these things are, okay? So what's going to happen is that therefore this implies that the integral from negative infinity to infinity of x squared over 1 plus x to the 4th dx is going to be 2 pi I times this plus this, right? So the 2 pi I times this thing is going to be a negative, right? So it's going to be a 2 pi. And then the I over here turns into a negative, so it's going to be negative. So I have an I, and an I turns into a negative 1 over 4. Pull that 4 out as well, actually, so we'll pull that 4 out as well. And I'm going to have a negative e to the I 3 pi over 4. Good. And then if I hit that with, I'm going to get a positive, right? So I have a positive, then e to the I, that's a negative, of course, right? E to the I negative I pi over 4. Okay, good. And so this is going to be what? This is going to be pi over 2, right? Pi over 2. And then where is negative 3 pi over 4? So negative 3 pi over 4 is in what quadrant over here? So that's going to be in the third quadrant. So this is going to be positive, positive. So it's going to be 1 over root 2 plus I over root 2. Okay, good. And then negative pi over 4 is where? That's in this quadrant down over here, right? So that's going to be a what? That's going to be a plus 1 over root 2 minus I over root 2. Of course, the i's are going to cancel out, and you can get 2 over root 2, so the 2 is going to cancel. Right, so this is going to be 2 over root 2, so this is just going to be pi over the square root of 2. Beautiful, right? So of course, it took a little bit of work involved in working with some of the complex numbers in the circle and making sure our trig identities are right, looking at moduli and figuring out what quadrant you're in. But it shows you the real power of this formula for computing a simple pole, the residue of a simple pole. Very, very, very useful and very powerful formula, right? Then what I like to do when I have these problems over here is I always like to take the problems, whenever I have e to the I something, if there's an e to the I in the denominator by itself, I like to make it do its conjugate, right, and put it up in the numerator, right? Then the rest of it is just how sharp are you with your trigonometry, right? So it's just a little bit of trigonometry, but you know the answer has to be real, right? So I knew that the i's were going to cancel out. So I said to make sure that the real terms were the right sign and the right balance as a non-negative quantity, and lo and behold, by quickly computing the trigonometric values, I was able to deduce what the value of this integral was by using the residue theorem. Very powerful result, which should be used all the time in computing these improper integrals in a complex variables course. Thank you very much.